They call it a floating airport. It is not floating. Nothing about it floats. The entire structure sits on more than 3,000 pillars driven down through the water, through the seabed, and into the bedrock underneath. What China actually built in Jinzhou Bay is stranger than a floating runway. They took 21 square kilometers of open sea, 4.5 kilometers off the coast, and turned it into ground, solid ground, engineered to carry 4 runways, a terminal larger than most city centers, and 80 million people a year. The reclamation is finished. The island exists. You can see it from orbit. And it took 15 years to get that far. When it opens, it will be the largest offshore airport ever built, larger in area than Hong Kong International and larger than Kansai in Japan. 4 runways, a terminal of 900,000 square meters, 80 million passengers a year, none of which is possible unless the ground underneath behaves. And manufactured ground has a long history of not behaving. The reason this project exists comes down to a problem that most large cities eventually run into. Dalian is a port city of roughly 8 million people on the southern tip of the Liaodong Peninsula in northeastern China. Its existing airport, Zhoushuizi, has been operating since 1924, back when the territory was leased to Japan. That airport is boxed in. The city grew around it over a century, and there is no room left to expand. No space for another runway, no space for a bigger terminal, no space for the cargo capacity a port city that size needs. There is also a detail about Zhoushuizi that shapes the whole situation. It has been used for both military and commercial flights for its entire existence. An airport shared with the military has less flexibility in scheduling, less freedom in expansion, and a ceiling on how much civilian traffic it can absorb. Dalian was operating a century-old shared airfield in a city of 8 million people that wanted to be a regional hub for Northeast Asia. The gap between what the city needed and what the airport could deliver kept widening. The obvious solution is to build a new airport somewhere with room. Dalian sits on a peninsula. The land is constrained on 3 sides by water and on the 4th by terrain and existing development. There was no good site. China has formed here. The country has been reclaiming land from the sea for decades, and it operates the dredging fleet to do it at scale. If the constraint is land and you have the equipment to manufacture land, the constraint changes shape. So the decision was to stop looking for land and make some. The site chosen was the eastern waters of Jinzhou Bay in the Bohai Sea, shallow enough to reclaim, close enough to the city to connect, far enough out that the airport would never be boxed in again. The finished island covers roughly 21 square kilometers, which is about 8 square miles. For comparison, that is larger than Hong Kong International Airport, which is also built on reclaimed land, and larger than Kansai in Japan, which is the most famous artificial island airport in the world. When it is complete, Dalian Jinzhouwan will be the largest offshore airport ever built. It will also be the first airport in mainland China built on an artificial island. Hong Kong has one, Japan has several. Mainland China, until this project, did not. That matters for a practical reason beyond national firsts. It means there was no domestic precedent to copy. Every decision on this project had to be made by people who had not done it before, using experience borrowed from other countries and adapted to a different seabed, a different climate, and a different set of storms. Now here is the part that determines whether a project like this works or fails, and it happens before anything visible gets constructed. You cannot simply dump material into the sea and build on top of it. Reclaimed land is made of fill, sand, rock, dredged sediment, whatever is available in the volume required. That material arrives loose, saturated, and full of voids between the particles. Put weight on it and it compresses. The surface drops. That process is called settlement, and it does not happen quickly or evenly. It continues for years, sometimes decades, and it does not happen at the same rate across the whole site because the seabed underneath is not uniform. Uneven settlement is what destroys airports. Think about what the surface has to survive. An aircraft on approach is aiming at a strip of pavement using instruments calibrated to an assumed geometry. The runway lights, the glide slope, the touchdown zone markings all assume the surface is where the design says it is. If one end of the runway drops 15 centimeters relative to the other over a decade, none of those systems is describing reality anymore. And you cannot fix it by resurfacing. Adding material adds weight, and weight is what caused the settlement in the first place. A runway has to be flat. Not approximately flat, flat to tolerances measured in millimeters over its entire length. Because an aircraft touching down at 250 kilometers per hour on a surface with a dip in it is an aircraft in trouble. And the world already has a warning about exactly this. Kansai International Airport opened in Japan in 1994, built on an artificial island in Osaka Bay. The engineers knew the seabed there was soft clay and predicted the island would settle. They designed for it. It settled more than they predicted, by a lot. The island sank far beyond the design figure, and it has kept sinking ever since. Kansai has jackable columns built into its terminal, specifically so crews can raise sections of the building as the ground beneath drops. That maintenance has been running for 3 decades and has cost enormous sums. The Kansai experience changed how the industry approaches this. It proved that soft ground under a reclaimed island can behave differently from the prediction, and that once construction is finished, your options for correcting it are limited and expensive. That is the outcome Dalian had to avoid, which is why the foundation strategy is different, and it is the single most important engineering decision in the entire project. More than 3,000 pillars were driven through the reclaimed fill, through the natural seabed sediment below it, and into solid rock underneath. Understand what that means structurally. The heavy loads are not resting on the reclaimed material at all. The fill creates the surface. The pillars carry the weight down past every layer that could compress and transfer it into bedrock that will not move. The island is not a pile of sand holding up an airport. It is a pile of sand with 3,000 legs through it, standing on stone. Driving those pillars is its own operation. Each one has to reach competent rock, and the depth to rock is not the same across 21 square kilometers. Some are shorter, some are much longer, and everyone has to be verified as actually bearing before anything is built on top of it. The equipment for that work floats. Piling rigs mounted on barges, positioned by satellite, driving through water and fill and sediment into stone thousands of times across an area the size of a small city. And the sequence matters. Piling into fill that is still actively settling produces a different result from piling into fill that has stabilized. Getting the order wrong means either waiting years for settlement to finish or accepting that some pillars will end up carrying load differently than designed. That is the kind of decision that does not show up in any photograph of the project and determines whether it works. The reclamation itself took far longer than anyone planned. Work began around 2011, then it stopped. The project stalled for years, waiting on national government approval, and construction on the reclamation appears to have been largely paused from around 2016. The original target opening date of 2018 came and went with an unfinished island sitting in the bay. The pandemic added further delay. A stalled reclamation is a specific kind of problem. The material already placed does not wait. It continues settling, weathering, and being reshaped by currents and storms while the paperwork is resolved. Work that resumes after a multi-year pause is not resuming where it stopped. Conditions have to be resurveyed and in places redone. Reclamation was largely completed in 2024, 13 years after it started. For perspective on that number, Kansai's island was built in about 5 years. Hong Kong's Cheklap Kok platform took roughly 4. Dalian took 13, and most of the delay was administrative rather than technical. The dredgers were not the bottleneck, the approvals were. The methods used to build it were driven by a requirement that sounds impossible for a project involving millions of cubic meters of material. Engineers worked to centimeter-level accuracy across the placement of fill. The tools that made that possible are worth naming because they are the reason a project this size can be controlled at all. Digital monitoring systems tracking the state of the site continuously. Precision satellite positioning determining exactly where material lands. Drone survey measuring the growing island from above and comparing it against the design. None of that existed in usable form when Kansai was built. The ability to watch a reclamation happen in 3 dimensions, in near real time, and correct it as it goes is relatively recent. Deep foundation treatment has also been completed across a 77,000 square meter section of the reclamation, preparing the ground specifically for the terminal building's foundations. That is a targeted operation, strengthening the exact area that will carry the heaviest concentrated load on the island. The rest of the site does not need the same treatment. Runways spread load across a huge area. A terminal concentrates it. There is also a detail about this project that reflects a change in how these things get built. A microgrid was installed during construction, combining wind, solar, diesel generation, storage, and charging. It is expected to generate around 464,000 kilowatt hours annually and cut carbon dioxide output by roughly 410 tons a year. That is not a large number in the context of a project this size, but it exists, and 20 years ago, it would not have. The ecological work is being run alongside the construction rather than after it. Li Xiang, deputy commander of the Dalian Airport Engineering Headquarters, described the artificial island as more than just a platform for the airport, noting that ecological protection and restoration are proceeding at the same time as the build. In one recent period, 850 trees were planted on the island, along with more than 40,000 square meters of landscaping and hardened green space. Trees on an island that did not exist 15 years ago, growing in soil that was placed there by dredger. Planting on reclaimed marine land is harder than it sounds. The material is often saline, low in organic content, and drains differently from natural soil. Getting anything to survive requires importing growing medium, managing salt, and irrigating continuously until root systems establish. It is a small part of the budget and an outsized part of whether the island reads as a place rather than a platform. With the island built, the buildings could finally start. In September 2025, China State Construction Engineering Corporation announced that a consortium had won the contract for the terminal, the elevated approach bridge, and supporting facilities. In June 2026, China's Civil Aviation Authority and the Dalian city government jointly approved the flight area and supporting works design. Those approvals matter more than they sound. They lock in the technical standards, the construction plan, and the investment scale. Until they exist, nothing above ground can proceed with certainty. The scale of what is now being built is difficult to hold in your head. The final layout calls for 4 runways in a terminal complex reaching 900,000 square meters. The airport is designed to handle the Airbus A380, which is the largest passenger aircraft in service, and requires runway length, pavement strength, and taxiway geometry that most airports cannot provide. In its long-term configuration, the airport is planned to handle up to 80 million passengers per year, 1.65 million tons of cargo, and around 540,000 aircraft movements. Those are numbers in the range of the busiest airports on the planet. The first phase is smaller, and the reported figures vary depending on the source. Some cite an initial terminal of 400,000 square meters, with 2 runways and capacity for 43 million passengers. Others cite 31 million passengers and 650,000 tons of cargo for the opening stage. The variation is normal for a project still under construction. The final numbers are what get quoted. The phased numbers change as the plan develops. It is worth flagging that distinction because it applies to every mega project. The headline capacity is the design ceiling, reached only if every phase gets built. The opening capacity is what actually exists on day one. Those two numbers are frequently reported as if they were the same thing, and they rarely are. But there is a category of problem with an offshore airport that has nothing to do with runways or terminals, and it is the part that separates a working airport from an expensive island. An airport 4.5 kilometers offshore is only useful if people and cargo can reach it. That means the project is not just an airport, it is a transport link, a power supply, a water supply, a drainage system, and an emergency access route, all of which have to cross open water. Every one of those is a potential single point of failure. If the bridge is closed, the airport is unreachable. If the power connection fails, an island with no grid behind it has nothing to fall back on. If a storm cuts access, there is no alternative route around it. That is why flood control and drainage are treated as primary design elements rather than utilities. A low-lying artificial island in a coastal bay has to move water off itself continuously and survive storm surge without flooding the very ground it stands on. Rain that falls on a natural landscape soaks in or runs to a river. Rain that falls on an artificial island falls on engineered fill surrounded by sea on all sides. There is nowhere for it to go except a system that was built to move it. And the Bohai Sea is not a calm body of water. Northeast China gets serious winter weather, and a bay is exactly the geometry that concentrates storm surge rather than dissipating it. The elevated approach bridge that appeared in the 2025 contract is not a convenience. It is the lifeline. The opening date has moved several times. The original plan was 2018. That passed during the approval stall. Current reporting points to the first phase opening around 2035, with some sources citing 2030 for full operation. 15 years from the start of reclamation to a finished island. Another decade, roughly, to a working airport. There is a specific risk in a timeline that long, and it is not engineering. Aviation demand forecasts made in 2011 were describing a different world. Aircraft types change. Route networks change. The economics of hub and spoke versus point-to-point flying change. An airport designed against one set of assumptions may open into another. That does not make the project wrong. It means the capacity figures being quoted today are a bet on what air travel looks like in the 2040s, placed by people working in the 2020s on a plan drawn in the 2010s, which puts the total timeline somewhere around a quarter of a century, from first dredger to first passenger. That is the honest cost of this approach, and it is worth stating clearly because the headline version of these projects rarely includes it. Building an airport on reclaimed land is not faster than building one on land. It is dramatically slower. It is more expensive. It requires foundation engineering that a normal site would never need, permanent monitoring that a normal site would never need, and connections to the mainland that a normal site would simply have. The reason to do it anyway is that Dalian had no alternative that worked. The existing airport cannot grow. The peninsula has no suitable site. The city needs air capacity to function as a regional hub in Northeast Asia. When those three things are true at the same time, the sea stops being an obstacle and becomes the only remaining option. There is a wider pattern here that Dalian is only one example of. At the end of 2024, China had more than 260 airports in operation, with 22 new ones under construction, representing over $20 billion of investment. Dalian Jinzhouwan is the most extreme of them, but it is not an isolated project. It is one entry in a national build-out, which means the engineering developed here does not stay here. The foundation methods, the survey techniques, the settlement monitoring, all of it becomes reference material for the next coastal city that runs out of land. Stand back and look at what is actually out there right now. 21 square kilometers of ground that was open water 15 years ago. 3,000 pillars driven through it into bedrock, 850 trees growing on it, survey drones flying over it, contractors building a terminal on it. 4.5 kilometers offshore, in a bay in the Bohai Sea, there is an island that did not exist, waiting for an airport that has not opened. It is not floating. It is standing on the bottom of the sea, holding itself above the water, waiting for the first aircraft to land on ground that used to be ocean.